students. Today we'll go for the introductory lecture on digital electronics. I myself M. N. Jadhav from KKWAK Polytechnic. Now, basically at the beginning we'll go for the logic gates. There are three categories of the logic gates. First one is called the basic logic gates, universal logic gates, and other logic gates. In basic logic gates, we'll go to study the AND gate, NOT gate, OR gate, and in universal logic gates, we have to study for NAND gate, NOR gate, and the remaining gates are XOR gate and XNOR gates. Now, here the table is there for all the combinational gates. At the beginning, we'll go for AND gate. The symbol for the AND gate is shown here, and the function for the AND gate is y is equal to a into b. Here that is nothing but the multiplication of input two variables. Now here say actually in digital electronics we have to use two numbers only, 1 and 0. So here the combinations for two variables are 0 and 1. Here we'll go for if both the inputs are 0 0, then by default our output y is equal to a into b, that is 0 into 0 is equal to 0 here. Now secondly, if the value of variable a is 0 and the value of variable b is 1, then the multiplication 0 into 1 is equal to 0. So our variable x output is equal to 0. Similarly, the another combination we are assuming here a is equal to 1, b is equal to 0. So our output 1 into 0 is 0. And finally, the last combination, both input variables a and b are 1 1. Then the product is 1 into 1 is equal to 1. Here we are showing the truth table. In the same way, we have to go for the truth tables here. Now here for OR gate, the output is x is equal to a plus b. That means the addition of the two inputs. But we have to do this in binary additions terms. Now here we will go for the third gate, that is inverter, or it is another name, is called the Higgs inverter gate or the NOT gate. Here there is only one input and the output is the inverse of the input. If input is 0, then the output is 1, and if the input is 1, the output is 0. Similarly, we have to go for NAND gate. Here the combination output x is equal to a into b total bar, and for the same we have to go for the truth table. Similarly, for NOR gate, the term output x is equal to a plus b total bar. The truth table for the same is here, XOR gate and XNOR gate. Now we'll go for the next slide. Here I show the combinations of all logic ICs. We'll go for any one example here. Let us consider this particular IC. The IC number is 7400 and the IC name is called as the NAND gate IC. The other name given for the same is quad NAND gate. That indicates in this IC it is a 14-pin IC with 4 NAND gates. So the name quad is given here. Each NAND gate having 2 inputs and 1 output. Let us consider this one gate. Here pin number 1 is the input, pin number 2 is the input, and pin number 3 is the output. Similarly, if we consider this gate, here pin number 4 is input, pin number 5 is input, and 6 is output. Pin number 7 is used for ground, and pin number 14 is used for VCC. In the same way, we have to go for the pin details of the remaining logic IC gates. Now, here we will see which are the universal gates, or what is the meaning of universal gates. Universal gates are nothing but the gates with the help of this one we can build any other logic gates. That is, from NAND gate and NOR gate we can build the AND gate, the OR gate, and the NOT gate. Now here the implementations, as already we observed, NAND gate is a universal gate. So using this NAND gate, we can build here NOT gate. Simply short both the inputs of the NAND gate. Similarly, using NAND gate, we build here the AND gate. And thirdly, using again these 3 NAND gates, we can build the OR gate. Similarly, we called NOR gate as a universal. Here, these are the examples. Using NOR gate, we built NOT gate. Using NOR gate, we built AND gate, and using NOR gate we built here the OR gate. Similarly, Here in this particulars, if again we convert one NOR gate, then again we can modify the logic circuits here. Now we'll go in digital electronics. What is Boolean algebra? Boolean algebra is nothing but there are some terms and the conditions in which basically the NAND gates, OR gate and the NOT gate terminology is going to used. Here is the tabular representations of the Boolean algebra. Here let us see. X is the variable. You can assume any variable, rather say A or something else. Here we consider the variable X. So X plus 0 is equal to X. X into 0 is equal to 0. This is nothing but in the form of your AND gate, that is multiplication terms, and this is in the form of OR gate, that is addition terms. Now here we'll see for the third one. X plus 1 is equal to 1, x into 1 is equal to x. In the same way, here we are considering the x bar. Again we are making the bar of the same variables. We get the output x here. Here the usefulness of this table, why we are using this Boolean algebra. It is used to simplify the Boolean functions. Also we can minimize any term or the given equations in digital electronics. Here we'll see again what is De Morgan's theorem. So in De Morgan's theorem, here we are considering two variables, x and y. Here we'll see for the term x into y bar is equal to x plus y total bar. Means here we are making the invert of the two inputs, that is x bar here, y bar here, and we get the output. It is nothing but the NOR gate output, that is x plus y bar. Similarly, the another De Morgan's theorem in which we are considering again the two variables x and y. So this is nothing but the addition, x bar plus y bar is equal to x into y bar. That indicates the inputs are nothing but the OR gates and the output is the NAND gate. Here in digital electronics, there are the conversions of the numbers. We can convert the decimal number to binary as well as the binary number to decimal. Similarly, decimal number to hex numbers and decimal numbers to octal numbers also, or the combinations of wire. Now here we consider simple examples converting the decimal number to binary. A simple number we are considering 53 and we have to convert this in binary. So let us divide this number by 2 and at the end we get the conversions, that is 0 0 1 1 0 1 0 1. Similarly, if we consider the binary number and we want to convert in decimal, now what is the procedure? Start from the last digit and move, that means starts from the right side and move to the left side. And let us see, we are starting from this 0 number, that is 2 to the power 0 into this multiplier 0 plus 2 to the power 1 into this multiplier 1 and so on. So the number 1 0 0 1 1 0 1 1 1 0, this binary number converted into decimal as 154. Here we'll go a lookup table for the same. So in this let us will see what is the relation between various number systems. So here these are our decimal numbers 0, 1, 2, 3 and so on. Now the binary numbers are here 0, 1, 1, 0, 1, 1, 1, 0, 0 and so on. Here the octal numbers. So basically in octal numbers, the numbers used are 0 to 7 and after 7 again the number starts from 1, 0 and so on. Similarly, in hexadecimals we are using the number from 0 to 9 and after 9 the decimal 10 is equivalent to hexadecimal alphabetic number A and so on. After this introductions of your conversions of the codes system or the numbers, we'll go what is flip-flop. Flip-flop is nothing but one kind of bistable multivibrator and it is a sequential circuit which gives the outputs in the form of 1 or 0, that is they are complement of each other and denoted by the numbers or the variables q and q bar. Here we'll see what are the types of flip-flops. So first one is SR flip-flop. Basically the flip-flops are used with the help of NAND gate and the NOR gate. Then second, clocked SR flip-flop, JK flip-flop, T flip-flop, D flip-flop and master slave triggered flip-flop. Here we'll go in detail with their truth tables and the symbol for the same. Firstly we'll go for SR flip-flop. So here we are considering the example using NOR gate. So there are two inputs S and R. S stands for set, R stands for reset. If both the inputs are 0, 0, then we say that there is no change in the output. That is, we are considering only one variable q and the another q bar is a complement for the same. So this is the truth table for SR flip-flop. If S is equal to 0, then our output q is equal to 0. This state is called the reset state. If the value of S is equal to 1, then our output q is equal to 1. This is called as the set state. And the last stage, S is equal to R is equal to 1. Then this state is called as the invalid state. Now, this is the representations along with the truth table. In short, SR stands for set and reset. Here, we'll go for the another flip-flop, that is JK flip-flop. This name is given by the scientist Jack Kilby. Now here again, the condition of S is equal to R is equal to 1 is overcome here. We are going to see again there are two variables J and K as inputs, and we are expecting the outputs in the form of Q and Q bar, which are complements of each other, and this is the truth table for the same. After that we'll go for D flip-flop. In D flip-flop there is only one input. It is also called as a data flip-flop, or we may say it is a delay flip-flop. Here we are considering one input 0 and the output is 0 again. After D flip-flop we will go at the end the T flip-flop. T flip-flop, the name is given as the toggle flip-flop. The output is the complement of the previous states in this T type of flip-flop. Thank you.